Guys, so we're continuing with our videos for the preparation for the FRM 5313 course, okay? And what we did last time, we talked about derivatives. I gave you some examples. What I'm going to do to talk about right now, I'm going to talk about matrices and linear algebra. And during the course, you will understand the extreme importance of this to risk and to risk and to statistics and whatever. Okay. So let's start by refreshing where the matrices are coming from. So let's say that you have one equation, one variable. So this is actually very easy to solve. You just need to take, so you want to solve for x, you just need to take 5 and take it to the other direction. So you have x equals 6 minus 5 equals to 1. Now let's say that you have two variables. Let's say you have 2x plus 3y equals 5 and 4x plus 7y equals to 10. How do you solve such a system? So there are two ways to do it. The first way is to do what we call back substitution. I'm going to show you a little bit different way. So how do you do that? So what you want to do, you want to eliminate the 4x from the second equation. And how do you do that? You just take the second equation and you subtract 2 times the first equation. So what do we get here? Here you get 4x minus 2 times 2x equals 0. So because 4 minus 2 is 0. And here you have 7y minus 3y times 2, which is going to be y. And here you are going to get 10 minus 5 times 2 equals to 10, to 0. OK? So what you are going to get here is as follows. You will get the following equation. Now this equation, 2x plus 3y equals 5, stays the same. The second equation actually will transform into y equals 0. OK? Because 10 minus 5 times 2 equals 0, 7y minus 3 times y equals y, and 4x minus 2 times 2x equals 0. So you will get automatically one solution, which is y equals 0. OK? Now you can actually solve for x. You can solve for x in two ways. Either you are going to use this equation or this equation. So if we use this equation, you're going to get that 4x plus 7y equals 10, and we know that y equals 0, so you're going to get here 4x equals to plus 7y, 7 times 0 equals 10, and here you're going to get that x equals 2.5. And indeed, if you substitute here, you will get the same result, because you have here 2 times 2.5 plus 3 times 0 equals 5. Now, we did it on the equations, but we can actually isolate the coefficients and do it on the coefficients themselves. So we're going to have something like this, 2, 3, 4, 5. And whatever we did here, we can do on the coefficients. So when we take the second row, and we subtract the first row times 2, we're going to get something like of the form 2, 3, 0, 0 and 5, and here we're going to have, sorry, it's 7 here, yeah? We're going to have 0, 1. OK? So this is a matrix that represents this new equation, this new system of equations. So what is this system of equations? Now you multiply by xy. So you have 2x plus 3y equals, and now here you are going to have 5. And here you are going to have y equals 0. And what you can do here, you can add another column, which is going to represent the coefficients 10 and 5. OK? So now you can actually add here another column here, which will represent the coefficients 0. When you do that, you will get 0, 5. Is this clear why? Because it's 10 minus 5 times 2. So you're doing elementary operations on the rows themselves. OK? So now, this creature, this innocent-looking table, is called a matrix. And, you know, side by side with the invention of calculus, the invention of linear algebra is one of the biggest breakthroughs that we have in math and in general. Because without linear algebra, just like without calculus, we wouldn't have iPhones, nothing that all the technology that is surrounded by us, that we're surrounded by. Okay? These are called matrices, and you know what we did here, we did elementary operations on matrices. Okay? So we can so this table is going to be called matrix, and we did the elementary operations on matrices. Now, how can we do it in general? So in general, here we have a matrix with how many? We have a matrix with 2 rows and 2 columns. So we will say that this is a matrix 2 by 2. Here, if we add 5, 10, we still have 2 rows and we have only 3 columns. So the new matrix, this matrix, is going to be called 2 by 3 matrix. So this entire matrix is 2 by 3. This matrix in a circle is 2 by 2. Okay? In general, we can have a table of n by n of m columns or n rows. So how do we denote that? We will denote it in general like this: A11, A12, A13, yada, 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 until A1n. So we have n columns. And now the second one is A21, A22, until A2n. And then the third one is A31, A32, until A3n. So what you have here, okay, is that the first one is a row and the second one is a column. So if you want to have a second column and a third row, you are going to have something of the form A23. This is going to be second column and third row. Sorry, wow, second row and third column. Okay? Very easy. Now, and you go until the end, you have am1 until amn. So this matrix is going to be m rows, and you have n columns. Okay, so overall you are going to have m by n matrix. Okay? So that's all there is to it. Now, there is a very nice geometrical interpretation of matrices. Okay? Think about the following situation, where you have a matrix of this form. It looks very scary, but hopefully you will see that it's not very scary. So you have cosine theta, sine theta, okay? And then you have minus sine theta, cosine theta. Okay, and now what you want to do, you want to consider this matrix in the following way. So if we have the xy axis, let's take that this is going to be the vector 1, 0, and this is going to be the vector 0, 1. Okay? Now I remind you that if you have a trigonometric function, one of the definitions of the trigonometric function, that if you have a circle like this, okay, this point, the radius is 1, radius is 1. This point, which is, which is characterized by theta, has the coordinates cosine theta, sine theta. Now, what you want to do here, you want to understand what happens with these two vectors if you rotate them. So if you rotate this vector by an angle of theta, you're going to get cosine theta, sine theta. You're going to get this guy, which is cosine theta, sine theta. Okay? What are you going to get if you rotate this vector? So it's like this. You are going to get a vector like this. So this is going to be 180 minus theta. And then, I hope that you remember from your high school days, it's minus sine theta, cosine theta. So what you are having here is a very interesting phenomenon. Okay? This matrix somehow decodes what happens with those vectors. How can we think about this in a more conceptual way? Well, we can think about these vectors 1, 0 and 0, 1 also as matrices. Okay? So this vector is 1, 0. How many columns? It has one column, and it has two rows. So it's 2 by 1 vector. And then cosine theta, sine theta encodes what happens with this vector. So if I'm looking on 1, 0, I discover, okay, that this is going to be cosine theta, sine theta. Now, how can I actually get this without remembering this? Okay? So that's a trick here. If you multiply now element by element. So you can say, okay, if I have a vector like this, I'm going to say that in order to get my cosine theta, sine theta, I'm going to take this guy, cosine theta. Sorry about that. I'm going to get this guy, cosine theta, and multiply by 1. And here I'm going to get this guy and multiply by 0. So I'm getting here cosine theta times 1 plus sine theta times 0 is going to be cosine theta. Okay, and here I'm going to get minus sine theta times 1 plus cosine theta times 0. How do I get this? Because I'm taking this element multiplying by this element, and I'm taking this element multiplying by this element. So the first element in this row is going to be multiplied by the first element in this column. And the second element in this row is going to be multiplied by the second element of this column. And lo and behold, what do you get? You get that this matrix, when you okay, now if you look here, how do we get this? Okay? If you look here, how do we get this? Okay? You can see exactly that you take cosine theta times 1 and minus sine theta times 0, you get cosine theta. Yeah, so I kind of mix the signs, so sorry about that. Okay, so cosine theta sine theta is going to be cosine theta times 1 times minus sine theta times 0, so you get cosine theta. And here you're getting cosine theta times 1 plus cosine theta times 0, you're getting sine theta. So when you take this matrix, you multiply by this vector, you get the vector cosine theta sine theta. So it means that this matrix, that lists the elements, encodes this rotation. How about the second vector? Is the same story. You have cosine theta sine theta minus sine theta cosine theta, and now instead of multiplying by 0, 1, you multiply by 0, 1, right? So what do you get here? And once again, like this, you get cosine theta times 0 minus sine theta times 1, so you're getting minus sine theta. And here you're getting sine theta times 0 plus cosine theta times 1, you're getting cosine theta. Okay? So what you are having here, that this matrix encodes the rotation of those two vectors, of 1, 0 and 0, 1. Now, if you have any other vector, you can actually immediately tell to which coordinates this rotation by theta will move him. How do you know that? Let's say you have AB. Okay, so you know now. So now you are going to use the same trick. So you are going to have cosine theta minus sine theta. And here you are going to have sine theta cosine theta. And now you're going to multiply by AB. Okay, so what will you get? You're going to get A cosine theta times A. So the first element multiplied by the first, so A cosine theta, plus minus sine times B. So it's minus B times sine theta. And the second vector is this times this plus this times this. So it's sine theta times A plus cosine theta times B. So any other vector that you have, okay, you encode where it will go by the rotation, you actually can find its coordinates using this matrix. Okay? So these matrices, what they do, they encode transformation of the plane. A 2 by 2 matrix, let's say 2 columns and 2 rows, encodes transformation of the plane. Okay? And now what you want to do, you want to generalize it. You want to generalize it to the n-dimensional space. So how does a dimensional, how, let's say, 4-dimensional space will look like? It will be basically just 4 coordinates. A1, A2, A3, and A4. Okay? This is going to be your vector. How can you think about this vector geometrically? Well, think about like a 4-dimensional axis. Okay? This is 1, 0. This is 0, 1. This is, so you have basically these vectors 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 0, 1. Okay? And what you have here is basically projections to each one. So for example, A1 will be the coordinate of the first vector. A2 will be the coordinate of the second vector. A3 will be the coordinate of the third vector, and A4 will be the coordinate of the fourth vector. It will be projections. Okay? So you have A1, A2, A3, A4. And now if you have, let's say, a 4x4 matrix, let's say A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, and A41, A42, A43, A44, like this. And then you multiply by this. How do you multiply? Well, this is not going to be that challenging. We just need to erase a little bit. So sorry about that I need to erase, but I need to write somewhere, right? So, okay, I erased. And now I'm having A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, and A41, A42, A43, A44. Okay? I multiply now by this vector. Let's change the A's to B's, so we're going to have B1, B2, B3, B4. Okay? And what am I going to get? So how do I multiply it? I'm going to say that this is going to be A11, B1, plus A12, B2, plus A13, B3, plus A14, B4. And this is going to be the first coordinate of the transformation. So you have this vector, and you transform it into a vector with these coordinates. Just like you have in a rotation. In a rotation, you have the vector 1, 0, and it transforms into cosine theta minus sine theta, or something like that, right? Cosine theta, sine theta. Okay, so you have this vector, and you have this transform. So it's exactly the same thing. But now you don't need to think about just transforms. It can be any other transformation. Okay? And then you have A21, A21, B1, plus A22, B2, plus A23, B3, plus A24, B4. So I think you get the idea. Okay? And then you go until 4x4 matrix. Okay? So you have a vector where you have a vector with 4 coordinates, you have another vector with 4 coordinates. So basically you can think about matrices, okay, as encoding certain transformation of n-dimensional space. You can think about matrices not just tables, but you can think about them as real objects like you can see here. Because it takes every vector, any vector that you have, and you just does something to it. Now, what kind of properties that transformations have? This is what we call linear transformations. Okay? And what are those linear transformations? What kind of properties they have? So the first property, that if you have two vectors, v1 plus v2, okay, and remember, this is how we represent vectors, it is going to be basically the sum of the transformations. And if you take and multiply the vector by a constant, you're going to have the transformation times the constant times the transformation. So for example, you can actually think about this in this situation where you have cosine theta sine theta. Okay? You have cosine theta sine theta. This is the image of the vector. So if you have two vectors, let's say, I don't know, you have, let's say, two vectors, A1, B1, and A2, B2, and you take this matrix, you multiply, you apply in these vectors, you have that, you see that the coordinate of AB is A cosine theta minus B sine theta. What will be the coordinate, let's say, of A1 plus A2? Well, it's going to be A1 plus A2 cosine theta minus B1 plus B2 sine theta. Okay? So you can see now that you can actually break it down. You can say that this is going to be A1 cosine theta minus B1 sine theta plus A2 cosine theta minus B1 sine theta. So this guy is a transformation of the vector A1, B1, and this guy is a transformation of the vector A2, B2. Okay? So you see that the sum of the transformation equals to the transformations of the sum. Okay? This kind of transformations, these kind of changes of plane are called linear transformations. Now, what do we have here? Okay, so what does it mean that if you have, let's say, m by n matrix, what kind of transformation it represents from what space to what space? Okay, so let's think about this a little bit. Let's look at an example. Say we have 2 by 3. So if A1, 1, A1, 2, A1, 3, and you have A2, 1, A2, 2, A2, 3, and now you want to multiply it by a two-dimensional vector. Let's say you multiply it by B1, B2. What will be the result? Where the result is going to be? The result is going to be what? B1, B2, B3. Okay, so what will be the result? The result will be as follows. A11, B1, plus A12, B2, plus A13, B3. And here you are going to have A21, B1, plus A22, B2, plus A23, B3. Okay? This is according to our convention, right? So we have this matrix, and then you multiply by a three-dimensional vector, you get a two-dimensional vector, okay? So then 3 is a number of columns. And 2 is a number of rows. So you can say now that if you have an m matrix, it's just a transformation from an n-dimensional space that we will denote by Rn into an m-dimensional space which we denote by Rm. Okay? So in this particular example, let's say, let's consider this example with numbers. What we're going to have is as follows. Here we're going to have, let's say, numbers 1, 2, 3, 4, 5, 6. And now we're going to have here, let's say, the vector 6, 5. 6, 5, 1. How we are going now to multiply this guy by this guy? So we're going to have 1 times 6 plus 2 times 5 plus 3 times 1. This is the result of the first one. And the second one will be 4 times 6 plus 5 times 5 plus 6 times 1. So 1 times 6 plus 6 plus 10 plus 3, 6 plus 10 plus 3 equals 19. And here we are going to have 24 plus 25 plus 6. So we are going to have 24 plus 6, 30 plus 25 is going to be 55. So the result, the two-dimensional vector is represented by the coordinates 19, 55. Okay? That's all there is to it. Okay? It's actually a very clear geometrical, a very clear link between those tables and linear transformations. And everything you can say about matrices will translate into linear transformations, and everything you can say about linear transformation translate into matrices. Let me give you another example. Why is it true? Okay? Let me give you another example. Why is it true? So for example, We talked about composition in previous lecture. We talked about composition of functions. When we talked about the chain rule, right? So we said that g of f of x prime equals to g prime f of x times f prime of x. That's what we talked about last time. Now, what does it have to do with matrices? And so now what we want to do, we want to compose linear transformations. Okay, so what does it mean to compose linear transformations? So it means that if you have two linear transformations, let's say T1 from Rn to Rm, and T2 from Rm to RL, okay? Let's say you have something like that. What it means is what you want to do now, you want to take now transformation from Rn to RL. So how would you compose it? So let's say you have T. Let's say that you have a vector 2, 3, 1, 2, 3, and T1 of 1 to 3. Let's say n equals 3, m equals 2. Okay, in our example. So this will move, let's say, to a vector of the form 5, 6. And now T1, T2 is going to take your R2 into R4. So you have a two-dimensional vector, but you are going to multiply just like here. You're going to have a four-dimensional vector. So 2 dimensions to 4 dimensions, and let's say that this 5, 6, this transformation will take it to 1, 2, 3, 4. So then you know that T1 composed with T2. So T1 first, T2 second of the vector 1, 2, 3 is going to be now the vector 1, 2, 3, 4. Okay? So this is what we call composition of linear transformation. What does it correspond in matrices? Well, it corresponds in matrices to multiplication of matrices. Okay? So composition, if you want to translate composition into matrices, composition goes into matrix multiplication. How do we talk about matrix multiplication? What is matrix multiplication? Okay? What is matrix multiplication? How do you do that? Okay, so let's take an example, and then we'll have a formula. So let's say that you have a matrix 1, 2, 3, 4, 5, 6. This is your first matrix. And you want to multiply it by a matrix, let's say 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? Let's see what will be the result. So how do we multiply it? So what we are doing, what we are going to do, we're going to multiply this like we multiply vectors, like we apply vectors. So the first column is going to be 1 times 3 plus 2 times 4 plus 3 times 5. This is going to be the first element. So it's going to be 1 times 3. So it's going to be 1 times 3, 3, plus 4, 8. So 3 plus 8 is 11, plus 15, 3 times 5 is 26. And now here we're doing the same story. We have 4 times 3, plus 5 times 4, plus 6 times 5. So here we are going to have 4 times 3, 12, plus 5 times 4, 20. So 12 plus 20, plus 30. So 32 plus 30 is going to be 62. So we took care of the first, of the first column. Now the second column is exactly the same thing. It's going to be 1 times 6 plus 2 times 7 plus 3 times 8. So it's going to be 6 plus 14 plus 24, which is going to be 44. So it's going to be 44 here. Okay? And now you're doing the same for the second one. So you have 4 times 6, 24, plus 5 times 7, 35. So it's 24 plus 35. plus 6 times 8, 48. So 24 plus 35 is 59, plus 48 is going to be 117. So the second one here is 117. Now the last one is 1 times 9 is 9 plus 20 plus 33. 9 plus 20 plus 33 is going to be 62, I think. And the last one is 4 times 9, 36, plus 50, 86, plus 66. So 86 plus 66 is 152. So here it is going to be 152. Okay, so what does it mean? It means that if you have a transformation here, and you compose it with a transformation here, this is the transformation you're going to get. Okay, you're going to get a transformation from 2. So here you are getting 2 times 3. Okay, so you're having a transformation from t. Okay, so you have a 2 times 3 here. You multiply it by this. Okay, you're going, and here you have a transformation 3 times 3. So you cancel this guy, and you're getting the a 2 by 3 matrix once again. So you are getting a transformation. So if you have t to R2 to R3, and here you're getting R3 to R, so from R3 to R2, and here you're getting R3 to R2 to R3 to R3. So when you compose, you're getting t from R3 to R2. Okay, so if you have here t from R2 to R3, and here you're having from R3 to R3, here you're getting here basically a transformation. So here, right, you multiply it by a R3 vector, let's say 1, 4, 5, and you're getting a vector, okay, which is going to be R2 vector. That's the idea, because this times this plus this times this plus this times this is going to give you a vector in R2. Okay, so overall, you start with a transformation. And you're ending up, and you compose, and you're ending up in a transformation in R2. Okay? Because this matrix is like this matrix. So okay. So first you compose. So you start with t. So you start with this transformation, right? So you go from R3 to R3, and then you overlay it with this transformation. So you are going to go from R3 to R2. So overall, you are going to have something from R3 to R2. I hope this is clear enough now, right? So this is the first one. This will correspond to the first transformation in the composition. This is going to be correspond to what T1, and T2 is going to correspond to that. Okay? So first you act with a vector. You take a vector and you make it into another R3 vector. Then you take this guy and you make it into R2 vector. Okay? Because when you take this guy, you multiply by 1, 4, 5. For example, you are getting 2-dimensional vector, not 3-dimensional vector, right? Because if you take 26 times 1 plus 44 times 4 plus 62 times 5, and here you are getting 62 times 1 plus 117 times 4 plus 152 times 5, you are going to get, it's going to be a complicated vector, but you are going to get a 2-dimensional vector. Okay? Now, what do we see here? We see here that the number of rows here, okay, that the number of columns equals to the number of rows. Okay? So you have here this times this, plus this times this, plus this times this. Okay? You have this times this, plus this times this, plus this times this. So here you have, the number of columns in the first one equals to number of rows in the second one. Okay? So it's actually very interesting because it gives you a very tight bound or constraint of how you multiply matrices. You cannot multiply matrices just by a whim. Okay? You have to multiply matrices in the following way. That they will correspond to a transformation composition. So if you have a transformation from Rm to Rl, and you have this is T2, and T1 from RL to Rn, the composition is going to be T2 composed with T1. It will go from Rm to Rn. Okay, so it means, okay, so you have a restriction on this L. How does it translate into matrices? Into matrices, it will translate when you multiply matrices. You're going to have that you can multiply matrices only if you have m times L and L times n matrix. And what will be the formula for that? So if you have a Aij, okay, and you have B K M, let's say. No, not M, I don't like M. Q, let's say. Okay? So then, A is a new CIQ equals to sum of J goes from 1 to whatever, let's say to L. Okay? Aij B JQ. So you see what happens? This index changes. This index stays the same. And this is exactly corresponds to this product, right? So it's if here, for example, I equals 1 and Q equals 1. So here you will say, OK, I will take the first row multiplied by the first column. 1 times 3 plus 2 times 4 plus 3 times 5. And this will correspond to your J. Because I here is a row, and here Q is a column. OK? And for example, for this one, OK, I is going to be 2, second row. And let's say we're still with the first column, so Q equals 1. So once again, Aij, Bjq, it means that you are actually multiplying this element-wise, like I showed you before. Okay, but the idea behind that, okay, how to remember this product, you take this matrix and you just apply to vectors. Okay, and then the vectors will give you, will give you a new table automatically. This guy, 2662, is just taking this vector, this matrix, and applying it on the vector 3, 4, 5. This guy, for example, 44, is just taking the first vector and applying it on 6, 7, 8. 117 is to taking this row and applying it on 6, 7, 8, etc., etc., etc. Okay? So basically, so what we discover here that matrix multiplication there is a madness there is a method in the madness. Why is it defined like that? Because it wants to actually correspond to composition of linear or of linear transformations. So you basically have a very tight geometrical meaning for this multiplication. Okay? Now, moving forward. Let's talk about the notion of a volume. So this is something which is very important, which corresponds to something in matrices, which is called the determinant. And you should think about, for example, of this form, something like that. So as this parallelepiped, right? Let's say the coordinates of the parallelepiped, whatever it is, let's say is generated by two vectors, this and this. So it's A1, A2, and B1, B2. What will be the area of this guy? Well, there is a very beautiful formula. And this point, for example, is going to be A1 plus A2 and B1 plus B2. So it's right. It's not a square. It's not like that. It's actually crooked because in a square you are going to have something of the form A0, B0, or 0. Sorry, vice versa. A0, 0B. Okay. What will be the volume of this guy expressed through those vectors? And this is going to be something of this form. So it's A1, A2, B1, B2. And then we're going to have something of this form. The formula is A1 B2 minus A2 times B1. Okay, so if this vector, let's say, is 1, 2, and this vector is going to be 3, 4, the area of this guy is going to be, okay, so we have 1, 2, let's say 3, 4, is going to be vice versa. 1, 2. Okay, so let's look on a square. So let's say we have this square. Okay, so it's then here those two guys will be 0. So we have A1 0, and here we have 0 B1. So then it's going to be A1 times B1, exactly what you would expect. Okay, because if this is A0 and B0, then the area of this guy is just A times B, because this is a width and this is a height. Okay, so this guy, this expression is a straightforward generalization of this expression. All right, that's all there is to it. Now, can you somehow define this in an n-dimensional space? And why is it used for algebra? Okay, because volume. Now, what happens here if those two guys are on the same line? If those two guys are on the same line, okay, then the volume of this guy is 0, right? So if A1, B1, and A2, B2 are on the same line, so it means that, what does it mean that they are on the same line? So let's say that this is A1, B1. Sorry. This is A1, this is B1. So this is A1, B1. And now you do, to here, it's A2, B2. So you know that C times A1 equals A2, and C times B1 equals B2. And now, substitute here. So you're going to have A1, CA1, and here you're going to have B2, B1, CB1. And now you're going to have the following. You're going to have, by definition, A1, B2 minus A2, B1. You're going to have A1 times CB1 minus B1 times CA1, which is going to be 0. Okay? So if those two guys are on the same line, you're getting 0. That's all there is to it. Okay? That's all there is to it. Okay, so what it tells you, okay, is that those vectors are dependent on each other. Here, okay, they are independent on each other because you can take the first one, multiply by a constant, and you get a second one. Can we generalize this dependency notion into higher spaces? Of course. If you have, let's say, three vectors, A1, A2, A3, and here you have B1, B2, B3, and you also have X1, Y1, X1, X2, X3. So these are three-dimensional vectors, okay? You can actually think about them as follows. If you have three vectors like this, okay? So what is the dependencies? Dependency is as follows. You have two constants, C1 and C2, such that so you can say that X1, X2, X3 equals to C1 times A1 plus C2 times B1 plus C3 plus C2 times B1, okay? So this is going to be for X1. X2 is going to be C1 times A2 plus C2 times B2. And X3 is going to be C1 times A3 plus C2 times B3. Okay. In matrix form, you can think about this also in matrix form. You can say that if you have a vector x1, x2, x3, okay, and here you have those vectors a1, a2, a3, and b1, B2, B3, you want to take and multiply by a matrix, or you want to take and multiply by something of the form C1, C2. So then this times this plus this times this will be x1. This times this plus this times this will be x2. And this times this time, and C1 times A3 plus C times B3 will be equal to x3. Let's take an example. Say we have a vector 1, 2, 3. And here we have 4, 5, 7. And now let's add it together. So it's going to be 1 plus 4 is 5. 2 plus 5 is 7. And then 3 plus 7 is 10. So then 5, 7, 10 is going to depend on those two vectors. What will be the coefficient C1, C2? C1 equals C2 equals to 1. What does it mean geometrically to be dependent in a three-dimensional space? Well, if you have those vectors, if you have these two vectors, 1, 2, 3, and 4, 5, 7, they span a plane, right? You can think about, you know, if you have in 3 dimensions, you have two guys like this, there is one plane that contains them, and it will contain the third vector, then it means that you have dependency, okay? So basically then you won't have, if you want to create a cube, you won't be able to, because two vectors collapse into a plane, and the third vector is in a plane, so the cube is going to degenerate into a triangle or something like that. That's all there is to it, okay? In general, what is dependency in n-dimensional space? So if you have basically, let's say A1, A2, A3, yada, 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 AN. And then you have, let's say, another vector, B1, B2, until Bn. And then you have another, all these vectors, let's say, X1, X2, until Xn, okay? And then you have a vector Y1, Yn, so then it means that you have a dependency, if and only if you have constants C1. Let's say that here you have, I don't know, k vectors. Okay? So it means here that you have basically a constant C1, C2, Ck, such that C1, A1, plus C2, B1, plus Ck, X1, equals to Y1, then C1, A2, plus C2, B2, this is B1, C2, B2, plus yada, 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 Ck times Xn equals to Y2, etc., etc. So you can see here that you have n coordinates, but in n coordinates you can have a k vector, k dependencies, right? So okay, now in an n, if you have n coordinates, if you have basically n coordinates, then you have exactly n independent vectors, n vectors which are not dependent. So what are those vectors? It's 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, etc., etc., 0, 0, 0, 1. Okay? And how do we see that those vectors are independent? Let's take an example in a three-dimensional case, and the proof is the same for n dimensions. Okay? So if you have 1, 0, 0, 0, 1, 0, and then here you have another vector 0, 0, 1, and suppose you are saying that they are dependent. So what does it mean that they are dependent? It means that you should have C1, C2 such that C1 times the first vector plus C2 times the second vector equals the third vector. So C1, 0, 1, 0, 0, here you have 0, 1, 0, must be equal to 0, 0, 0, to 0, 0, 1. And look what happens here. Okay, so you have C1 times 1 plus C2 times 0. This is your first coordinate. So you're going to have C1 times 1 plus C2 times 0 equals to 0. This goes away, so you have C1 equals 0. Okay, so the first coordinate must be 0. The second coordinate is the same, but now you're looking at the second one. So you have C1 times 0 plus C2 times 1. And this is going to be 0 because the third one is 0. So you have automatically that C2 equals 0. So these vectors are not dependent because both coefficients here are 0. They must be different from 0 in order for these guys to be dependent. Okay? What the determinant says, so going back to the determinant quantifies, if you have a matrix, first of all, you have to have a square matrix. For not square matrix, the determinant do not work. So if you have A11, A12, A1n, A21, A22, A2n, AN1, ANN, this is your matrix, okay? The determinant of this matrix will say that if this is 0, it means that you have dependency. And if determinant of this matrix is not 0, these vectors are independent. How do you calculate the determinant? Well, there is a trick to calculate the determinant. And let me show you a trick. So the first thing you do, for each matrix, remove the row and the column of one element. Okay, so let's say that you have something of this form, A11, A12, A21, A22, A21, A22. In order to calculate this determinant of this matrix, what you want to do, you want to look on this, and you want to erase the first row and the first column. So then you say, okay, what is left is A22. So I'm going to take A11, and I'm going to multiply it by A22. Okay, and the sign is going to be the sum of those 1 and 1. So 1 plus 1 is 2, so this is going to be positive. Now you are saying, okay, I remove the first row and the first column, in the first element. Now I'm going to go to the second element in the column, and I'm going to remove this. So what is left? A12, right? So I'm going to have A22 times A12. And what will be my sign? The sign will be minus. Why? Because this guy, it's 2 plus 1 is 3. So it's odd. So the rule is, if you take this guy and you multiply by whatever is left, if the sum of the indices is an odd number, you are taking a minus. If the sum of the indices is an even number, you are taking a plus. So for example, let's calculate it on a 3 by 3 thing. Okay, so we have A11, A12, A13, A21, A22, A23, and A31, A32, A33. And now you're going to take and you're going to look on the computation with respect to the first row, to the first column. So the first thing you do, you remove this, and you have A11, and you multiply by the determinant of this guy, which we know what it is. It's A22 times A33 minus A32 minus A11 times A32 times A23. So this is going to be the first element of the determinant. Now the second one, you want to remove this guy and this guy. So what will be left will be a matrix A12, A13, A32, A33, right? Because you remove the first row and the first column. So what will survive will be this guy and this guy. Okay, and now you're taking A21, but with a minus sign, and you're going to say, okay, I have A21 times, and now what is the determinant of this guy? Okay, so we already calculated it. It's going to be A12 times A33 minus A21 times A32 times A13. Okay, because you take A21, you multiply by the determinant of this guy, so I already opened the brackets. And now the third one, okay, it's plus 3 plus 1. So now you're removing this and this. You are going to have what will survive, hopefully. What will survive is going to be A12, A13, A22, A23. Okay, so you are having here A31 times A12 times A1, A23 minus A22 times A13. Okay? So this is the determinant of this matrix. And if the determinant is not 0, it means that those three vectors are independent. So what it means is that you cannot express this vector as C1 times this one plus C2 times this one. You cannot express this one as C1 of this one plus C3 and this one. That's how it works. Okay? So you can't, unfortunately, what you can't do, the determinant tells you, okay, that you have a volume, that you are, you know, that these guys are actually in a cube. Because if this guy wouldn't be in a cube, okay, this volume will be 0. And now what you want to do, you continue like this. So now if you have a 4 by 4 matrix, you play the same game. Because now you know how to calculate 3 by 3 matrix. So now you are going to calculate 4 by 4 matrix relying on a 3 by 3 matrix. Okay? So you're going to have here A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, and then A41, A42, A43, A44. And now you say, okay, I'm going to develop with respect to the first column. So you're going to have this times this. So you take A11 multiplied by the determinant of this matrix. Then you are going to remove this guy, and you take A21 multiplied by the determinant of whatever survives, etc., etc., etc. And now if this is not 0, okay, what it means is that you have that it's not that you have dependent vectors. Okay? Okay? Good. Now, why is it useful? Because it enables us to have a very nice algorithm to solve linear equations. And this is done using a device which is called an inverse matrix. So what is an inverse matrix? So if you have so this is once again valid only for n by n matrices. So if 5 by 5 matrices, these are called, by the way, square matrices. Okay? So what you are having here, for example, you have something like this. So if you have a matrix which is basically n by n matrix, and the determinant of matrix is not 0, you can find a matrix B such that A times B equals what we call the identity matrix. What is the identity matrix? The identity matrix is a matrix where you have ones on the diagonal. So this is so I is the following matrix. It's actually 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Okay? These are basically what we call the identity matrix. Why is it the identity matrix? Well, if you take any vector, let's say we have 1, 0, 0, 0, 1, 0, 0, 0, 0, and now we multiply by a vector a, b, c. So what do we get? 1 times a plus 0 times b plus 0 times c, so it's a. 0 times a plus 1 times b plus 0 times c is b. 0 times a plus 0 times b plus 1 times c is c, right? So the vector doesn't move. That's why it's called the identity matrix. Because if you take a linear transformation which is corresponds to it, you are going to have the same vector. You are going to have the identity transformation. Okay? And if you have a matrix, a times b equals I, it means that if a corresponds to a linear transformation, okay, so this b, which we denote by A inverse, okay, basically when you compose it with a with this inverse, you are getting the identity. So it actually gets back to the vector you started with. So for example, let's say that you have, in a two-dimensional space, you have basically the same cosine theta sine theta minus cosine minus theta sine theta cosine theta. By the way, what is the determinant of this matrix? Let's compute. So it's this times this minus this times this. So it's cosine theta times cosine theta minus sine theta times sine theta. This equals to cosine squared theta plus sine squared theta, which is equals to 1. So the determinant of this matrix is 1, and of course it means that those vectors are not dependent. Okay? Now, so what is going to be the inverse transformation? How do we think about the inverse transformation? So in this case, if you know that 1, 0, we said goes to cosine theta sine theta, what it means is that here, okay, cosine, the vector cosine theta sine theta, under the inverse transformation, read my lips, inverse transformation is going to go back to the vector 1, 0. Okay? And intuitively it is correct, because what is the inverse transformation? If you rotate it around with the angle of theta, you go back with the angle of minus theta. Okay? So it's clear that this vector is going to go back to the unit vector 1, 0. That's all there is to it. Okay, but now let's say that you have a system of linear equations with a square matrix. So say you have something of this. So symbolically, okay. So let's take an example of an inverse matrix. Let's say that you have something of this form. Let's say you have a matrix 1. Before we do that, let's look on 1, 2, 3, 4. Okay? What is going to be, so, or in general, let's have a 2 by 2 matrix. We have A, B, C, D. What is going to be an inverse of the matrix A, B, C, D? Okay? So the inverse of the matrix A, B, C, D is going to be, so if this is A inverse is going to be what? Well, it is going to be A D divided by A D minus BC. Okay? Then minus C divided by AD minus BC. Okay? Here is going to be, and here it is going to be basically A divided by AD minus BC. And here it is going to be minus B divided by AD minus BC. So now let's take this matrix and multiply by this matrix. What are we going to get? So we're going to have here this times this, so it's going to be A times D, minus B times C, divided by AD minus BC, which is going to be 1, correct? Now we're going to take and multiply by this column. So it's going to be this times this plus this times this. So it's going to be minus AB divided by AD minus BC, plus AB divided by AD minus BC, which is going to be 0. So here we have the matrix 1, 0. Now we are looking here. So once again, it's C minus B plus D minus A, right? No, it's, sorry, this times this first. This times this. You see, I'm confused, so of course it's very confusing. Now it's C times D, so it's C times D minus D times C divided by AD minus BC, which is going, this is going to be 0. And the last one is going to be minus BC plus AD divided by AD minus BC, which is going to be 1. Okay? So exactly we are getting 1, 0, 0, 1. Now, observe that AD minus BC is the determinant of this matrix, so the determinant of A. We could actually write this using the determinant. We could actually write this a little bit more in a little bit more compact fashion. We could write this thing as follows. We could say that the inverse matrix of A, B, C, D is as follows. It's going to be D divided by the determinant of A, then minus B divided by the determinant of A, then minus C divided by the determinant of A, and then we're going to have A divided by the determinant of A. Okay? So you must see that the determinant is not 0. So if the determinant is 0, no inverse matrix. If the determinant is not 0, so if the determinant is not 0, then you have the inverse matrices, and this is true in general as well. This is very true in general, that if A, and this would denote the determinant, so if you have A, this is the determinant of A, this is not 0, means that if and only if A has an inverse. All right? So here, for example, for this one, let's apply the formula for this one. What do we get? Okay, this is interesting. So AD minus BC is going to be what? 1 times 4 minus 3, so 4 minus 6 is minus 2. So now you're going to have D, which is 4 divided by minus 2, so it's minus 2, right? 4 divided by minus 2. D divided by the determinant. Now here we have minus C divided by the determinant, so it's going to be minus 3 divided by 4 by 2. Okay? It's 2 here. Yeah, because the determinant is negative, so it's plus 3 divided by 2. Okay, now here minus B divided by the determinant of A. This is going to be minus B divided by the determinant of A is 1. And here we're going to have 4 divided by AD minus BC. I'm going to get probably, it's going to be A, sorry, it's going to be A divided by the determinant. So here I'm going to have minus half. Okay? So 1 times minus 2 plus 2 times 3 halves is 1. 1 times 1 plus 2 times minus half is 0. 3 times minus 2 plus 4 times 3 over 2 is 0, right? And 3 times 1 minus 4 times half minus half is actually 1. So when you multiply this matrix by this matrix, you are actually getting this. Okay? Now, what does it have to do with the solution of linear equations? So if you have a matrix, so if you have a matrix A, okay, and you want to solve, so if you have A11, A12, blah, 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 A1n, A21, A22, A2n, and here you have A1 until A and n, and you multiply by the vector x1 to xn to get, and you want to solve for b1 to bn, okay, you can write this in a very compact form as like this. So this is x, this is your vector, and b, this is your vector. So you have n by n times n times 1, you're getting n times 1. Okay? N by n times n times 1, you're getting n times 1. Right? So now, if you have an inverse matrix, you can say, okay, let me apply an inverse matrix on both sides. I'm not going to change anything. So it's going to be A inverse times A times x equals to A inverse times B. But what is A inverse times A? This is identity. Identity times x is x, so you are getting the solution automatically. It's very convenient. Okay, going back to this example, say you want to solve now 1, 2, 3, 4, okay, times xy equals, let's say, to 7, 8. Okay. So how would you proceed using this? So let's solve it in a regular way. So regular way, we have the system of equations x plus 2y equals 7, and here we have 3x plus 4y equals 8. And what you want to do now, you want to actually look on the, you want to take the second row and subtract 3 times the first row. So you are getting here 3 minus 1 times 3, which is 0. And here we are getting 4 minus 2 times 3, which is minus 2. So here you are getting the following matrix. It's going to be 1, 2, and here you're getting 0, minus 2. And here what you are getting, 8 minus 7 times 3, it's 8 minus 21. You're getting here, here you are getting 7, and here you're getting 8 minus 7 times 3, you're getting minus 13. So here you have a minus 2 times y equals minus 13. Okay? So now so y equals to 6.5. Okay, what is x? What is going to be x here? So you can use the second equation, and you can say that you have 3x plus 4 times minus 6.5 equals to 8. Okay, so 4 times minus 6.5 is going to be 26. So it's 3x minus 26 equals 8. So it means that x equals to 34 divided by 3. Okay? And indeed, let's substitute it here, and let's see that it actually works. So you have here 34 divided by 3 minus 2 times 6.5. So 34 divided by 3 minus, did I do it right? Probably I messed up somewhere. So let's see, x plus 2y. So let's see once again. So it's x plus 2y equals 7, 3x plus 4y equals 8. So you have 3x minus, so 4y minus 2y is minus 2y, 8 minus 7 times 3 is minus 21. So it's minus 6.5. That's correct. And here you have 3x plus 4 minus 6.5. So it's 3x minus 26 equals to 8. 8 plus 26 equals 34. So it looks okay, 34 divided by 3. Okay, I'll leave you this as an exercise. Okay, let's now solve it using this. Let's see if we get the same result or not. So now we're getting minus 2, 1, 3 halves minus half. And what you want to do, you want to multiply it by your vector 7, 8. That's all. So what do we get here? It's here minus 2 times 7 minus 14 plus 1 plus 8 minus 14 plus 8. You're getting 6 minus 6. And here you are getting 3 halves times 7 minus half times 8. So it's 21 over 2 minus 4. So you are getting here 6.5. Okay, so I probably messed up the signs or something. So let's see if this works. So here we're going to get x plus 2y equals 7. So we said that it's minus 6 plus 2 times 6.5. This equals to 7. This is correct. And here we're getting 3 times, we said minus 6 plus 2 times 2 times, or 4 times, sorry. 4 times 6.5. Is it going to be 8? Well, 3 times minus 6 is minus 18, plus 4 times 6.5 is 26. So it's minus 18 plus 26 is going to be 8. That's it. So one way gave us the correct way. I don't understand what happened here. This I leave you as an exercise to find the mistake in my calculations. Why here I'm not getting the same thing? Probably because I messed up the signs. Yeah, because here you see 4y minus 2y minus 6y is minus 2. Okay, here's the problem, right? So it was 4y minus 6y, it was minus 2y, and here 8 minus 7 times 3 is 8 minus 21. It's minus 13. So it's 2x minus 2x equals minus 13. Not plus 2x, but minus 2x. So x equals minus 6.5. And now, when I'm using this, so it's 4 times minus 6.5, so it's 3x plus 4 times x.5. Once again, you're getting the correct result, because here you are getting 4 times 6.5, and then you subtract, you're getting here minus x equals minus 6. So all is well. All right? So what we covered today, we covered a lot of material. So we introduced matrices, we covered the determinant, we covered the inverse matrix, and we covered the geometrical meaning of matrices, okay, which is basically transformation in n-dimensional space, okay, and the composition of transformation in n-dimensional space corresponds to multiplication of matrices, okay? And then, when you have this equation Ax equals b, if you have A inverse, and only if you have A inverse, you can write it in this convenient way, and you can see that you actually get a solution in a very direct way. All right? So that's what I wanted to tell you, and hopefully that I'll see you in class. Thank you, and have a great day.